Here is my free fall reaction time project for Phys114 Fall 2013. I'm Bradley Wilmot, and here's my project. The first thing I'm going to show you is the equations for a free falling body. And the first is the distance that it falls is equal to 1/2 times the acceleration due to gravity times the time squared. So if we know the time, then we already know the acceleration due to gravity on Earth, and so all we need to do is square the time, multiply it by gravity, divide it by 2, and you can get the distance with that formula. And the second one comes from the first one, and so we can find the time by doing the square root of 2 times the distance divided by the acceleration due to gravity. So if we know the distance, we can easily find the time. And these equations are interchangeable in that if you take time, you can square this side, and that'll be time squared, and you'll have 2d over g. So you multiply the time squared by the g, and you have time squared times g, and then you divide d by 2, and you will get this if you solve that for d. And it works the other way as well. So using these equations, we can come up with these formulas that will give us the distance fallen using the reaction time. And here's an Excel chart from my file. You can see we have time in milliseconds all the way up to 430, and we have distance fallen in millimeters all the way up to 1,000. And this is just using the equation, and we can see that it's an exponential equation, where as the time increases, the distance increases exponentially. And you can see this in my Excel chart here, where we have a table. Time in milliseconds is just starting from 0, and we go up by increments of 10 milliseconds. And at 0, the distance is 0. And here you can see we have the equation for the distance related to the time. So distance is going to equal 1/2 times the acceleration due to gravity times the time, which is multiplied by 0.01 in order to keep the correct units, squared, and that will give us the distance. And then to keep the correct units, we multiply that by 10 to keep this in terms of millimeters. And you can see that equation works, and we have the table of values here that goes down to 400 or so milliseconds. And you can see we put that data in, and it gives us this graph. And the second equation is the one we're using for the reaction strip, which is solving that equation for t. And you can see this is an exponential decay function. It's a square root function, and over time, as the distance gets greater, the time is slowly decaying. So at 0, it'll be greater than it is from 0 to 20. It'll be a greater increase than it is from 900 to 1,000. But we can use this function in order to make our reaction strip, which is how I made my reaction strip. And here's the Excel file for that. We have the table here, and distance is in increments of 5 millimeters over there. And then we have this function for the time, which is the equation of the first one, which is 0.5 it's actually the square root of square root of 2d over g, but I cannot can see it is the square root of 2 times distance times 0.01, and that's to keep the units correct, divided by the acceleration due to gravity, and then multiplied by 1000 to keep the units right. So you can see that this is the equation that makes this graph, and it shows us how to make our reaction strip, because we make it with these increments of millimeters, and it gives us these reaction times. And the third Excel I have is the actual data from my reaction strip testing. And here we have all of my subjects laid out right here, numbered up to 20. And we have their 10 tries over here. And these are each of their reaction times in milliseconds. And you can see we took those and we calculated the mean times for each of those people, and then we counted the total mean, which was 151, and then we found the standard deviation of each one of those people, and then we found the average of the standard deviation, which is about 14, which is kind of bad, but since it was just a time strip, I can't expect it to be a really great way to measure it, but it was good enough. And so those are the accels. And for the Moon and Jupiter, the Moon's acceleration due to gravity is 1.62 meters per second squared, and for when a time strip would be falling towards the Moon, a person would have more time to grab it because it will accelerate toward the Moon slowly. Therefore, the less time, the time that they take to grab it, the strip will fall a smaller distance than it would on the Earth, which would lead them to get a larger reaction time using the same strip. And on Jupiter, the acceleration due to gravity on the surface is 26 meters per second squared. And if we use our reaction strip on Jupiter, the acceleration on the strip would be accelerated even more so than the Earth. So the strip would go faster through your hand, and so more distance would go by in the same time than it would on Earth. So your reaction time will actually seem like it's greater if you use the same strip that you used on Earth. And if measurements were made in an elevator moving upward or downward at 10 meters per second, then the measurements would not be affected because the elevator and everything inside the elevator is moving at a constant velocity along with everything else. So the reaction strip is also going to be moving upward or downward, so it will accelerate towards the Earth just as it would outside of the elevator. But to someone on the outside of the elevator looking in, it would be totally different. And in an elevator accelerating upward at 10 meters per second squared, the reaction time would be longer because the elevator accelerates faster upward as the time strip accelerates downward. So as the elevator accelerates upward, the time strip falls farther because it's accelerating downward as the elevator accelerates upward. And when it falls farther, the reaction strip will look as though it will be caught at a farther distance. And in an elevator accelerating downward at 10 meters per second squared, the reaction time would be shorter because the elevator is accelerating downward at the same time the strip is accelerating downward. And since they're both accelerating downward, along with you, the person catching it, the strip won't move as far because the strip's acceleration goes along with the elevator's acceleration, so the distance that the reaction time happens will be much shorter. And if a person had a very slow 2-second reaction time, then a card strip will be very unreasonable because it would have to fall about 20 meters before it is caught. And I don't know who this person is, but I don't think you can make a time strip longer than 20 meters just so that they can try to catch it. But you could just use a stopwatch because it can produce good results around 2 seconds if you just use your stopwatch and measure the reaction time. But otherwise, you could somehow slow the acceleration of the time strip enough so that the person could catch it. And then you wouldn't need to use the stopwatch, but you would need to change your equations to account for the slower acceleration of the time strip. And that is my project, the free fall reaction project for Clark Wellman in Physics 114 for fall 2013. Thank you.